Okay, let's continue on our journey through engineering aspects of computerized tomography. And the next aspect I want to consider is 3 dimensions. And up to this point, I imagined that everything we're looking at is just 2D. We're measuring in 2-dimensional planes. If we want to have a 3D measurement or 3D image, then we'll have to stack 2D images. And so that was the idea that we pursued up to this point. While that really is the way many computerized tomographs work, there is an alternative. And think of the following. Assume that we want to take a CT, a computer tomogram of this human over here, and assume that we have a radioactive source over here, and assume that we really want to have a 3D image. Now, what we could do is we could place a giant X-ray screen behind the human and measure along all the lines that come from this point where the point source over here is. So we have a giant X-ray screen behind the human, and we have an X-ray source over here, and we can measure along all lines that come from here and go through the human. Okay, so that gives rise to the so-called cone beam transform. And it's defined as the following, quite obvious after what I said. df of A and X, where A is the position of the X-ray source. I can measure along all rays that come from A. So I can, for every X, I can compute the integral from 0 to infinity f of A plus t times X dt. And that's at least true for all rays that go through the human, and for all other rays, the integral is 0 anyway. So I can assume that this can be measured for all X. Of course, we need a giant X-ray screen on the other side for this to work. Okay, so that's a reasonable definition. Now, I claim that the Fourier transform of df with respect to the second variable can easily be computed. And let's see how that is done. First of all, the Fourier transform does not exist in a classical way, so we have to do the usual thing. We take df, look for the corresponding distribution, that's TDF, take its Fourier transform, that's defined as TDF of phi hat. And from the definition of the embedding of functions into a distribution space, this is nothing but the integral over Rn df of A and psi f hat of psi d psi. I plug in the definition of df, then we get this one over here. I exchange the integrations over here. So this is integral from 0 to infinity, integral over Rn. And then I have something like f times the integral over Rn, f times phi hat. So using Parseval, I can exchange that. So I can take the integral over f hat times phi. That's what I have here. And but we need to take the Fourier transform with respect to this psi over here. And again, using the computation rules for the Fourier transform, which we derived in 4.2, we see that the Fourier transform of this function with respect to psi is nothing but r to the minus n e to the ia psi over r f hat of psi over r phi of psi d psi and dr. Okay, now let me again change. Let me change back the order of integration, and then this is the integral over Rn phi of psi, integral from 0 to infinity r to the minus n e to the ia psi over r. Everything is just left, and this is dr d psi. Okay, this is almost what I wanted to prove, only now I set r equal to 1 over rho, which means that for the integration constant, we have dr is 1 over rho squared, d rho. And so this is the same as the integral phi of psi. Inside the limits have to be adapted, but at 0 infinity again. So we again get the integral from 0 to infinity. R is 1 over rho, so this becomes rho to the n, but I have a rho to the minus 2 over here, so this becomes rho to the n minus 2 e to the ixi times rho. And it should be a times psi and times rho. And so this becomes the Fourier transform evaluated at rho times psi. Remember, rho is 1 over r, d rho d psi. And this is, and now what I have here, that's a distribution that is represented by the function in the integral 0 to infinity rho to the n minus 2 and so on. So the inner integral over here. And since this was df hat, then in fact, this is what I have here is df hat. And correctly, that should go up to here. Okay, so we can compute the Fourier transform of df with respect to the second variable. And now let's assume that the X-ray source is not fixed at some point, because we won't be able to reconstruct if we have just one fixed position of the X-ray source. But let's assume that it travels along a path. And that path should be A of lambda, where lambda is in 0, 1. And later I will assume that A is differential. And of course, we now want to look at n equals 3, right? So I'm fixing now n equals to 3, and the radioactive source is traveling through the space and is taking its measurements as I defined it before. So we measure df of a of lambda and x. Okay. Now I want to introduce Thuys condition, and that's something which may sound a little bit weird at the start. Assume that the support of f the support of f is known, right? I mean, we know where the human is, so that's the support of f. Take any function and take any element of the support, so that's a point where we want to reconstruct the function f. And take any direction theta, and we're in R3, so theta is now in S2. Now, take the plane that goes through X and is normal to theta. So that's the plane of all y that satisfy that y times theta is the same as x times theta. Okay, we say that a curve satisfies Thuys condition if for every x in the support of f and for every theta, for every direction theta, there is at least one point of the curve is in that plane. So for every plane that hits the support of f, there should be at least one point of the curve in that plane. And additionally, the plane should not be tangential to A in that point. So the tangent, which is given by the first derivative of the curve, times theta should not be 0. Okay, so all in all, for all x in the support and for all theta in S2, there should be a lambda, depending on theta and x, of course, such that A of lambda of theta and x is in E, and A prime of lambda of theta and x times theta is not equal to 0. Now, simple example, very simple example. The easiest thing that you can think of is you have a 3-dimensional object, and you just let the source circle around it. So the source path then would be a circle around that three-dimensional object, and that's what I tried to depict here. I hope you get the idea. The black thingy is the three-dimensional object, and the radioactive source travels around it on a circle. Now, does that satisfy Tui's condition? No, it doesn't, because take a horizontal plane. Let's assume that this circle is horizontal as well. So let's take any horizontal plane and move it a little bit down, like this plane over here. This definitely, the circle is up here. The plane is down here. It hits the support of F. It hits the object. So it is a permissible E, like we had above there, but there is no point of the curve is in this plane over here. So this does not satisfy Tui's condition, which is bad, right? I mean, that would be the easiest thing we can think of. So, and later we will show that we have reconstruction formulas whenever Tui's condition is satisfied. Unfortunately, in this situation, really there is no exact reconstruction formula. How could we how can we satisfy Tui's condition? Well, add a second curve like this one over here. Then you see, well, this like this straight line over here. And you see that now every horizontal plane hits that line over here. And in fact, now the Tui's condition is satisfied. Okay, so the theorem, why I'm bringing up that condition is the following theorem, and it says if Tui is satisfied, then F can be reconstructed from dF of AF lambda and X with lambda in 0, 1. So if we have the complete cone beam transform for this curve, for a curve which satisfies Tui's condition, then we can reconstruct. Okay, let's prove that. And the proof is surprisingly simple. I hope I didn't do anything wrong. Assume that X is in the support of F. If X is not in the support of F, then we know that f of X is 0 anyway. So let X in the support of F. We will prove this reconstruction formula, and we do it the following way. First of all, we start with f of x, and f of x is the inverse Fourier transform of the Fourier transform of x. So that's 2 pi to the minus 3 over 2 integral over R3 f hat of psi e to the minus ik ix psi d psi. And I think that should be a plus over here. Yes, and I'm using that in the next step. E to the ix psi d psi, so that's just writing down the inverse Fourier transform in 3 dimensions. Now we introduce polar coordinates, and we've seen that many times. So we write psi as r times theta, with r larger than 0. And of course, theta is now in S2 because we're on R3. And the integration constant is now no longer rho, but it's rho squared. So moving to polar coordinates, this is the same as the integral over S2, integral from 0 to infinity, rho squared, that's the constant over here, e to the I, well, x is rho, psi is rho times theta. So e to the I rho x times theta, f hat of rho times theta. Yes. Maybe that's why it was so simple. Of rho times theta, d rho d theta. Okay, now we for x is in x is in the support of f. So there is a lambda of theta and x, such that x times theta is the same as a of lambda of theta and x times theta. And I just plug that in. That's just the definition of, whoops, that's just a Tui's condition, right? I mean, it says that if x is in the support, then we have then there exists a lambda of theta and x such that this is the same, and I just plug this in over here. Okay, now let's forget about that for a second, and let's compute d over d lambda df hat of a of lambda and theta. Okay, that's the same as the d over d lambda, and that's the Fourier transform of df with respect to the second variable. And yeah, that with respect to the second variable. And I can just plug this in. Yeah, that's exactly what I just proved. And I take the formula for that, and that was d over d lambda. And I proved that this is the same as this one over here. Okay, I won't give a reason for that, but I take the d over d lambda in over here and take the derivative of this one with respect to lambda. Then that becomes the integral from 0 to infinity rho times, and now the derivative of this one with respect to lambda is rho squared. One is one rho, together with this one is rho squared. We have an I over here, and a of lambda, the derivative is a prime of lambda. And yeah, I take that out, and here we have the integral of 0 to infinity rho square. Okay, this one stays, so it's e to the I rho alpha of lambda times theta, f hat of rho times theta d rho. Okay, and there can, why we can take the derivative under the integral sign can be proved, but I'm not going to give you the reason here. Okay, so now we find that this over here, this seemingly complicated expression, is just the same as this one over here. So I can replace it, of course, choosing lambda as lambda of theta and x. And that means that we have f of x is the same as this one. And now I plug in this formula over here, and then we have that f of x is 2 pi to the minus 3 over 2 times 1 over I times the integral over S2. Now this becomes 1 over a prime of lambda, and as I said, I plug in lambda as lambda of theta and x. So this is 1 over a prime of lambda of theta and x times theta. And what is left is the d over d lambda df hat of af lambda and theta. And that's, of course, again evaluated at lambda of theta and x. Okay, so now we have a formula to compute f from df hat, where df hat is the Fourier transform of df with respect to the second variable. Now, we assume that df is measured along for all values in the second variable. So we can compute that Fourier transform over here. And of course, we can then also compute the derivative, and we can do the integral. And so that means that the f is uniquely determined by the values of df. Okay, so now we have a reconstruction formula for any source curve that that satisfies Tui's condition. And it turns out that Tui's condition is, in fact, it is needed. And so if Tui's condition is not fulfilled, then there is no reconstruction formula. And in fact, f is not uniquely defined by df. in a stable way. Okay, so this is one of the many reconstruction formulas that you can derive for 3D scanning. And I should add that this is a very simple one, which is not actually implemented. That's one thing. And the second thing, usually what is implemented in CT scanners is exactly the geometry that I just described. So they have the object, and then they let the radioactive source perform a curve, a circle around the object. And in fact, there is then no reconstruction formula, as I just mentioned, since that doesn't satisfy Tui's condition. But there is an approximate inversion formula known as FDK of Feldkamp, Davis, and Kress. But, well, I'm not going to mention this, but just for completeness, this is what is usually implemented in this type of scanners.